Yeah, okay, so let's start. Um, so this lecture will be mainly about few things which I didn't cover in my main lectures. So, but they're very important anyway. So remarks and examples. The first thing that I want to talk about is this. Before I start that, the first thing, let me just mention one thing. Recall that.
So we can't see anything on the screen.
Oh, you can't see anything. Oh, okay, fine. So
I
let
think so.
me
Can
just.
someone else confirm?
Yeah, it's not just.
Is it coming?
Sir, no. We can see this Android screen mirroring
Settings
option.
screen where it says screen
Yeah, the
mode and
No,
settings
but
screen, but not that.
not the actual. So I've already written a sentence. Can you see that?
no, there's no notebook.
Oh, there you can't see that. Okay, let me just try again. Well, I'm supposed to be sharing this. I don't know why. Okay, let me try one thing. I'll try to share whatever is on the whole desktop. Now, can you see it?
Yeah, we can see the desktop
Yes.
which has a notebook on it.
No, not that. I've written something, remarks and
Yeah.
examples.
Remarks
You
and
can see
examples,
this.
recall
Okay,
that.
fine. Yeah, all right. So recall that the space of linear transformations from Rn to Rm is isomorphic as a vector space to Rn times M. And also to M NMR, this space of M cross N matrices. So there are these three spaces, the space of linear transformations, Euclidean space of dimension n times m, and the space of M cross N matrices. They're all isomorphic to each other as vector spaces. Now, the thing is that let us take n equals m. This is not really necessary, but just for simplicity, let's take this. This is actually, in this case, we denote M and R by M and R. And right, the point is that we have at least two natural in some sense, natural norms in this setting. One is, of course, on Rn squared. Remember, I took n equals m, so I get Rn squared. On Rn squared, we have the Euclidean norm. On the space of linear transformations, we have the operator norm. Well, since we are identifying these spaces, Rn squared, the space of linear transformations and matrices, in effect, we have two different norms on the same vector space. So in this case, some issues will arise. For instance, so let's look at a more general setting. More generally, let's look at metric spaces. Consider metric spaces x dx Suppose we have a continuous map from x to y. Now, I change the metric on the domain and the range. Let d x, I'll put a 1, superscript 1. Be metrics on x and y. Well, I can still look at the same map. Now the question is, f from x dx1 to y dy1 still continuous? And the answer is no. It that's unreasonable to expect. And here's a simple example. So let's take the sets, underlying spaces sets to be x equal to y equal to r. Now the first metric, the dx and dy, I take to be just the absolute value, which is the usual distance on the real line. So in other words, this distance, etc. Now, what I'll do is I'll change the the second one. I'll change to be the new metric on the domain. I'll still keep to be the absolute value. But the other new metric on the target, I'll change to be this, the so-called discrete metric. So this is defined by dx dy1 of xy is equal to 1 if x is not equal to y, is equal to 0 if x equal to y. So I leave it to you to check that this is indeed a metric. Those three properties of a distance function are satisfied for this. Now, this is a very funny kind of metric in the following sense. Let's look at an open ball here. Let P belong to Y, R greater than 0. Then distance, then the ball of radius R, BPR, with respect to this discrete metric. Well, if R is strictly less than 1, you will be looking at all other points, all points X such that distance between P and X less than 1. For this metric, that can happen only if it is 0. The metric assumes only two values. So in that case, this would be 0, will be just the point P if R is less than 1. On the other hand, if R is greater than or equal to 1, then every other point has distance less than or equal to R is equal to all of Y if R is greater than or equal to 1. As a consequence, what happens is that therefore, now let's, this is as far as the metric is concerned. Now let's look at a function. We are, after all, interested in continuity, how the notion of continuity changes. Let f from R to R be the identity. F of x is just x. Of course, this is, if I regard it as a function, if I talk about continuity with respect to dx1, which is the absolute value function. Oops, this is, no, there's no 1 here. Dy. So remember that dx and dy were just the absolute value functions. So usual distance. So this is, of course, continuous. But what about f as a function dx1, which is still the absolute value function? But on the target, I have put the discrete metric. This is not continuous. The identity function is no longer continuous if I change the metric on the, for example, the target. And well, that's easy to see. I mean, for example, you can take the inverse image of an open set should be open, that characterization of continuous functions. As we saw, a ball of radius r, if r is less than 1, is just a singleton, but that's an open set. So singletons are open in the target. So the inverse image of a singleton would be just a single point in the domain, and that is certainly not open when with respect to the absolute value metric. So this simple example will show that. There is, so one has to be careful about this notion of continuity when we change metrics. Now, So we would like a simple criterion which will guarantee that even when we change metrics within a certain class, the notion of continuity does not change. So I leave the following to you as an exercise, homework. Prove the following. Suppose let's we say that two metrics D and D tilde on a set X are equivalent if there exist two constants C1, C2, positive constants, such that the distance with respect to the tilde metric is less than or equal to C2 dxy, greater than or equal to C1 dxy for all xy. The main point is the same constants C1 and C2 should work for all xy. So this, of course, we are not demanding that the two metrics are equal or even scalar multiples of each other, but almost scalar multiples of each other. If this happens, we say that the metrics are equivalent. This is the definition. This is not, of course, this is not, there's nothing to prove here. The proof part comes now. If dx is, and we write, yeah, so the notation is d is equivalent to d tilde. If dx is equivalent to dx1, suppose dx is equivalent to dx1 and dy is equivalent to dy1, then f from dx to dy dy is continuous if and only if x dx1 y dy1 is continuous. So in short, if you have equivalent metrics, then the notion of continuity does not change. Now, this is that's a very general statement, and it's a proof. I leave it to you to check that it's not difficult. So, but it'll it's a good test of your understanding of what it means. I mean, what is an open set in a metric space? What is continuity, etc. Actually, you don't even need to know what an open set is. You can even use the sequence definition of continuity. That will also work. Now, here is something which is more slightly more definitely more non-trivial. This what I just stated is for general metric spaces. There's not much involved there. Let's now turn our attention to metrics distance functions coming from norms. So we are now in the realm of vector spaces, finite dimensional vector spaces proposition. Let norm 1 and norm 2 be norms on, I'll just take Rn, and let D1 and D2 be the associated distance functions. Then D1 and D2 are automatically equivalent. So the moment we are on a finite dimensional vector space and the metrics are coming from norms, we don't have to worry about this issue of continuity changing if we work with one norm or another norm and so on. So let's, this one has more content than the previous thing that I asked you to prove, because we'll be using the fact that we are on a finite dimensional vector space very crucially here. Then D1 and D2, yeah, okay. So let me quickly sketch a proof of this. The first observation in order to prove this is, let you take some norm, be any norm on Rn. Then this norm as a function from Rn to R, actually it is Rn to 0 infinity, Rn to R is continuous. The second thing is that if this norm with a subscript E is the Euclidean norm, then there exists C1 and C2 both positive, such that norm with respect to our given arbitrary norm is less than or equal to C2 times the Euclidean norm of a vector greater than C1 times the Euclidean norm of that vector for all V in Rn. So what this says is that any norm on Rn is sort of approximately equal to the Euclidean norm, approximately in this sense. Another way of interpreting this is, if I take the ratio the given norm of a vector divided by Euclidean norm, that is bounded above and below by positive constants. So this is what approximately equal. If they were literally equal, of course, C1 and C2 would be 1. Or if they're scalar multiples, C1 would be equal to C2, but we don't need that. We just need to know that this ratio is bounded. And that will turn out to be enough. So let's prove this. Prove. The first part was a claim that any norm is automatically continuous as a function. Well, that's just so. Let's just calculate norm V minus W.
Can you share the statement of this first part?
The statement was that norm is continuous. Lemma, the first part is let this thing be any norm on Rn, then this norm is a continuous function.
Thanks.
Okay. So in fact, what I'm going to prove is it's uniformly continuous. So I'm going to make this difference, norm difference small. Oh, by the way, yeah, I should mention one thing here. When I say it's continuous, obviously, what does continuity mean here? Continuity with respect to the Euclidean distance on Rn. With respect to the Euclidean metric on Rn. Okay. So there's a background Euclidean metric. Now, given any norm, I just regard it as a function on Rn. The claim is that that function is continuous, keeping the background Euclidean metric in mind. So in short, what we want to, yeah, so let me just clarify this point. We will prove uniform continuity of the norm function i.e. We'll prove uniform continuity of the norm function, i.e. norm of v minus w given epsilon greater than 0, there exists delta greater than 0 such that norm of v minus w less than epsilon whenever. Now here's the main part. The whenever is, see, we are talking about continuity with keeping in mind the Euclidean metric. So the domain distance is the Euclidean distance. So this is what we'll prove. Okay. And so for that, yeah, well, to see this, we expand it in terms of coordinates. So V is summation Vi Ei I equals 1 to n. W is Wi Ei I equals 1 to n. Then norm of V minus W will be norm of summation Vi minus Wi Ei. Now I'll use the triangle. This is the one of the main properties of the norm. It is less than or equal to summation, and then I'll also use the scalar multiplication property of norm. Yeah. Then this norm EI, these are all positive numbers. There are finitely many of them. So it'll have a maximum. This set will have a maximum. I'll call it alpha. So alpha Vi minus, where alpha equal to the maximum of norm E1 all the way up to norm En. So what I have is norm V minus, so this is the main inequality. So I have this. And then, of course, as usual, we know that this modulus of Vi minus Ei. So therefore, if the Euclidean norm of V minus, this is small. So this is summation vi minus wi squared, whole thing under square root. If this is less than delta,
So you should write Euclidean norm.
oh yeah, right, thanks. Yeah, if this is equal to this, and if this is less than delta, then well, you square both sides and you will get each one will be less than delta, right? So this if this is less than, actually let's see. So yeah, in fact, at this point I won't elaborate on this. So you can complete the proof. Basically, if this is small, then each modulus of vi minus wi, each of those terms will be small. So you can use the smallness of this part here and get that norm of v minus w is small. Complete the proof by yourself. The main part here is just using a basis essentially. So here, here again, finite dimensionality has been used. That I had a basis and I could do all this stuff. And I could take the maximum, etc. Now but still this is finite dimensionality was used, but in a very mild sense. Now here finite dimensionality will be used in a more crucial sense. So the second part was that we want C1, C2 greater than 0 such that the norm of any vector is less than or equal to C2 times the Euclidean norm of that vector greater than C1 times the Euclidean norm of that vector. So for this, what we do is let's let's look at the unit sphere in Rn. Let Sn minus 1 equal to set of all V in Rn such that the Euclidean norm is 1. Now, let's restrict our norm function. Consider the restriction to just this unit sphere. And since we are on the unit sphere, the value 0 cannot be assumed by the norm. So it will have to be between 0 and infinity, the open interval 0 and infinity. We have already proved that the norm is continuous. Now, here's the main point. Sn minus 1 is compact. It's closed. Oh, here I made a mistake. I shouldn't have put E here. I should put E outside. Sn minus 1 is compact. The set of unit vectors in Euclidean space is compact because it's closed and bounded. Therefore, this norm function, and norm is continuous. Therefore, this norm function assumes its minimum and maximum. So there will be some C1 less than or equal to norm V less than or equal to C2 divided by norm. Oops, there's no C2. And this both of these are C1 is also positive because well, we know that the function norm is positive on the unit sphere, and since it assumes the minimum, it'll have to be some positive value. So this is the main part of the argument, that the unit sphere is compact, the norm is continuous. Any norm is continuous, so therefore one gets this. And then this is for all unit vectors, Euclidean unit vectors. That's the underlying assumption. Now, of course, from this, it's easy to get it for any vector whatsoever. So let V be arbitrary. Then I just take the unit vector in this direction, Euclidean unit vector. Set this one satisfies as unit norm, Euclidean unit norm. Therefore, I can apply this inequal, whatever I got, the bound I got for W, and I get W less than or equal to C2. Then you just multiply both sides by norm, Euclidean norm of V, and immediately you get which is what we wanted. Now that we have this, now let's return back to proof of the main proposition was that we had two norms on Rn. When I made that statement, I didn't even talk about Euclidean norm. I just said that I have two arbitrary norms, then I can find constants such that something happens and so on. In the process of, in the lemma, I brought in the Euclidean norm into the picture and it proved all this. But we are almost done because, so now we have two norms, norm 1 and norm 2. By the lemma, there exist A1, A2, B1, B2, such that norm 1 less than or equal to A2 times the Euclidean norm, A1 times the Euclidean norm, and for norm 2, I have a similar thing. From this, so you just, it's a matter of eliminating the Euclidean norm and just writing an inequality in terms of norm 1 and norm 2. So I leave it to you to do that, but it's quite easy. So for example, norm 2 will be, see, for norm 2 will be less than or equal to B2 times the Euclidean norm, but the Euclidean norm is less than or equal to A1 inverse of norm 1. So just combine that B2 A1 inverse of norm 1. Similarly, on the other side, norm 2 will be greater than or equal to B1 times the Euclidean norm, but that will be, now I go back to this side here, and then B1 A2 inverse of, oops, ran out of space. So I'll just, where was I? Yeah, norm B2 is greater than B1 A2 inverse. B1 A2 inverse of norm 1. So you can call this as C2, and this as C1, and you're done. So these two, you just eliminate the Euclidean norm and write it in inequality in terms of these. And the moment you have this, whatever I wrote here, the corresponding inequality for the distance functions will immediately follow. After all, the distance function d of xy is just supposed to be norm of x minus y. So this immediately implies that C1 d2 xy is less than or equal to, no, d1 d1 d2 xy less than or equal to C2 d1 xy for all x and y. So this is so what I proved just now, that any two, especially in this form, this thing, whatever I wrote here, is something that you will see mentioned often in any analysis course. If you are going to take any other analysis course, or even for that matter, topology course, you'll see this statement being made again and again. It's that any two norms on Rn are equivalent. And now we have a complete proof of that. Okay, so as I said, our main interest, why I even ventured into this is, I'm going to talk about, there are some lots of interesting examples where where the domain is the space of matrices itself, functions with. Before I move on to that, I should mention one more thing, which is that another corollary is that, first of all, continuity does not depend on which norm you take. And also differentiability, which involved norms, again does not depend on that. So let f from Rn to Rm suppose the notation becomes a bit unpleasant here. So suppose I have two different norms on Rn, and likewise I have two different norms on the target, put a M on Rm. Now I'll assume that these are equivalent norms on Rn and these equivalent norms on Rm. Then f is differentiable at P with respect to the first pair, norm 1 with respect to this, if and only if it is differentiable with respect to the second pair. So here I have 2 and then this. So again, this is just a simple exercise. There's nothing involved here. It's a simple exercise involving the definition of the derivative and playing around with inequalities. That's it. So I leave it to you to check this. Now comes the main point of doing all this jugglery. So let's take a concrete example. Now, so far, the role of the space of linear transformations or matrices, etc., is they somehow arise since the derivative was a linear transformation, they arise in a natural way. But the original function was on Rn. But the space of matrices itself can be regarded as a domain for other functions and very natural functions. For example, the determinant is a function from the space of matrices to the real line. One can ask, is it differentiable? What is its derivative? And so on. Now, one can do that. It's not that difficult. But before we do that, let's take some simple functions on where the domain is the space of matrices. And let's see if we can calculate the derivative of something like that. So here, the domain is the space of n cross n matrices, which we know is the Euclidean space can be identified with Rn squared. By the way, this identification of Rn squared arises, I mean, you can write down a basis of MnR consisting of n squared elements. I hope you know how to do that. Then it's just a basis element. The ijth basis element is the matrix consisting of all zeros everywhere except in the ijth place it will be 1. So those will form a basis. So once you write a basis, you know it's abstractly isomorphic to Rn squared. But actually, there's another straightforward way of doing this, which is if you take a n cross n matrix, I can map it to just a long n squared tuple of numbers. So I'll just, again, I have various choices. I can write down the columns side by side, or I can write the rows side by side. Let me stick with rows. A1n, etc. And then AN1, ANN. So actually, maybe I should write it, instead of writing it one below another, it's better if this is mapped to A11, A1n, AN1, ANN, which is an element of Rn squared. So this is a very concrete way of going back and forth between Euclidean space and the space of matrices. Right. So now let's, as I said, there are lots of natural real valued functions on real valued or the first example I'm going to give is not real valued. It is a function from MnR to itself. Let f from MNR to MNR. Remember, you should be always, in case you get confused, always keep in mind that MNR is just Euclidean space of dimension n squared. The point about using this notation MNR is that lots of functions which are very natural when I think of this n square tuple as a matrix will not appear natural at all when I just forget the matrix structure and write it as a long n square tuple. So for instance, here is something. So f of x is just x squared. Square matrix, and I multiply it with itself. This is a very natural, it's like the generalization of the quadratic function x squared to MNR. Now I want to claim that f is differentiable everywhere, and the derivative of f at a point A now, what is this derivative is going to be a linear map from the corresponding vector spaces. Now the vector space is Rn squared, again Rn squared, so I'll just write MNR to MNR. Is given by f prime A acting on H is AH plus HA. So the variable here is H. A is a fixed point, and the variable. Yeah, so this example at first sight might appear a bit confusing because I mean the derivative is the role being played by MNR is not this. One must not think of MNR as the space of linear transformations at this stage. It's just Euclidean space, but it has some nice different way of thinking about it, which enables us to, for example, multiply two vectors, two elements of Euclidean space via this for matrix multiplication, etc. So yeah, in fact, forget the linear transformation, MNR as space of linear transformation. Just think of it as matrices. That's then it will be less confusing. But the derivative anyway is going to be a linear transformation. Abstractly, it is given by this formula. By the way, if I think of the derivative, since the derivative is a linear transformation, it will itself have a matrix. Can someone tell me what the size of the matrix is going to be? This f prime A. What will be the size of the corresponding matrix? Anyone?
N square cross N square, right?
N squared cross N squared, correct. After all.
But do we really want to look at it like a two-dimensional matrix? As in
square matrix.
Yeah. Do we really want to look at it like that?
No, we don't. In fact, we don't want to do that. But just to keep track of things, I asked this question. We are not going to write down the matrix of this for sure. It'll be, I mean, there's no need, and it'll be a messy computation. So if, just to keep track of, to see whether you're following what is going on, I asked this question. Okay, so for us, the main thing is the derivative as a linear transformation is given by this nice simple formula. So let's see why, how we get this. Right, and also having made such a fuss about norms, I should remark that it doesn't see MNR as Euclidean space, so I have the option of working with the Euclidean norm. But I also have the option of working with the operator norm on MNR, which is another norm. So all that stuff that I said previously will ensure that for example, when I talk about derivative, it doesn't really matter which norm that I work with. I'll get the same answer. Actually, I should add one more small remark here. I said that in this corollary, I said f is differentiable with respect to one pair of norms if and only if it's differentiable with respect to another pair. The remark I have to add is not only is it differentiable, I'll get the same derivative as well. I mean, technically speaking, it could be differentiable with respect to different norms, but I might end up getting different notions of derivative. But that's not the case. The derivative as a linear transformation will continue to be the same property will hold for both norms. Anyway, the proof will show that, so I didn't say that. So let's see why this, so what do we have to, yeah, by the way, here I wrote down the answer, but how did I get this? So for that, let's calculate this f of a plus h minus f of a. This is a plus h squared minus a squared. Now remember, this is matrix multiplication, so you have to be a bit careful. It's not commutative. So you'll get a squared plus ah plus ha plus h squared minus a squared. So a squared cancels out. I'm left with ah plus ha plus h squared. And this is true for any h. A is fixed. So for any h, I have this. Now this will enable me to guess what the derivative is. See, the point is that when I take f of x plus h minus f of x, I'm supposed to get the linear part is supposed to be the derivative, linear in h. The other stuff is not supposed to matter. Higher order terms in h should not matter. So here it's clear enough that the linear part is this other, there are two parts here, this one and this. This is clearly not linear in h. This one is. So we guess that the derivative is this, and this should not play a role in the derivative. So in order to check our guess, so let us do the calculation. So f of a plus h minus f of a minus this linear part ah plus ha. I have to take the norm and I'll continue taking the operator norm and divide by norm h. Then I have to see that this limit goes to 0 as h goes to 0. Well, I've already done the numerator will be just norm of h squared divided by norm h. Now we'll use that nice property of the operator norm, that norm of AB less than or equal to norm A times norm B. That's one of the main reasons for using the operator norm. So this is less than or equal to norm H times norm H, which is norm H squared. Oh, no, this square was inside. Norm of H squared, it was inside. Then I got the square outside. and this is just norm H. So the upshot is that this quotient is less than or equal to norm H, which means that it goes to 0 as H goes to 0. So therefore, what does all this prove? This proves that this stuff, this linear transformation here is exactly the derivative. Therefore, f prime A acting on H is H plus HA. Now, there is nothing particularly significant about this square function. It's just one more polynomial, that's all. The more interesting and natural functions on matrices are, as I said, things like the determinant, and another one is, for example, transpose, operations that you can do on matrices. It'll turn out that almost all of pretty much anything you can think of will be differentiable. Finding the derivative is a different matter. It's not so obvious how to, for example, what would be the derivative of the determinant B? So here's another easy example. This is the last one, then I'll stop. F from MNR to R, f of x is trace of x. Now, I claim that even without doing any computations, one can say what the derivative of this is going to be based on something that we had discussed very early on when I talked about derivatives, when I introduced derivatives. So can someone tell me what the derivative of this will be? So what is f prime A? Now this will be a map from MNR to R. So what is this acting on H? You don't need to, the hint is that you don't need to do any computations.
Trace of H, maybe?
And why is that? You're right, but why is that? I mean, you can directly do it, of course, it's quite simple.
You can just.
But what is the property of the trace map as a function from MNR to R?
It's a linear map.
It's a linear map. The trace map is a linear map. And we have already seen that if you have a linear function, a linear transformation, its derivative is itself. It doesn't depend on which point you take the derivative at. You'll get the same thing, the same linear map at whatever point. So this is just trace of H. And you can see this directly also. I mean, you can just do f of x. Whatever I did in the previous example, you can do here and get this. Okay, so I went slightly past overtime, but this class of examples is not dealt with in Rudin. But nevertheless, it's a very important class of examples, especially if you study differential geometry or topology. Now, there is another book for those of you who are interested. It's not necessary that you look at this book, but for those who are interested, I would strongly recommend by Kumaresan. It's called A Course in Differential Geometry and Lie groups. just the zeroth chapter or the first chapter is relevant for us, where he talks about multivariable calculus. Now, if you are going to look at this book, I would just give one warning. He talks about normed vector spaces or even Banach spaces. Just ignore that. Just substitute Euclidean space wherever he talks about Banach space. If you do that, then this book is, you can have a look at the very first chapter. That has lots of nice examples like this. More examples of derivatives than the usual stuff that Rudin talks about. So, okay, let's stop here. Bye.
So, can you share the notes?
Yes, I'm going to put it up. I'll put the video. I recorded the video as well. Oh man, I didn't record the video. Okay, I'll just put up the notes.
Yes.
Yeah.